So let's have a look. So your pop quiz, you're just going to grade yourself right now. I'm not even going to keep track of it, just to make sure we're on our toes, okay? So we've got this professor, he's receiving emails, and we kept track of all the things, and we put them into, apparently the most emails he ever received ever was how many? 5. And the least he ever received ever was, well, of course, 0. And he received 1 sometimes, 2, 3, and 4 sometimes. So we looked at all the emails he's ever received in the world. None of them got deleted, okay? So none of these emails got deleted. We've got all of them in this table. We're supposed to figure out the expected number of emails first, okay? So that's the expected value of x. Well, first we have to define our random variable. If you don't define a random variable, you're going to be lost. So make sure you always define your random variable first. You might get away without not doing it sometimes. But what is x? Number of emails. Pretty simple. This time you might not have done it. If you are getting lost on a problem, it's probably because you really don't understand what is the random variable. That's one of the big reasons people get lost. So careful about that. All right, so expected value of x should be, how do I do it? You guys tell me the long way, because we're going to do it the long way and the calculator way. Long way, how do I do it? Each x sub I times the probability weight attached to it. So we're going to have 1 times 0.1. We're going to have 2 times 0.2. 3 times a quarter. 4 times 30%. And 5 times 10%. And we'll get it that way. They also asked for the standard deviation of emails. When we do standard deviation in situations like these, and for much of the year, honestly, we don't start by doing this standard deviation. We start by doing the variance. Okay, so we're going to find the variance of x, otherwise known as sigma squared of x, right? I like to write it like this sometimes because it reminds me that there's like a squared, which is going to be big time today. So I'm going to say x sub I minus, oh, I guess I need this number first. What'd you guys get? I'll trust you. 2.95? That's what I remember. And what should I put for units? Emails. That's the number of emails the professor can expect given this distribution, which I think makes sense because he gets 4 of them 30% of the time. The heavy weights are right here, so it should be somewhere near those heavy weights. That should make sense to you guys, yeah? Okay, so we got to go 0 minus 2.95 squared times its probability, which is 0.05, plus, then you'd have to do the next one, which is 1 minus the expected value squared times its probability. Plus, you got to do that for every one. I'm not going to write them all out. The last one we're going to have, though, is 5 minus 2.95 squared times 0.1. So what'd you guys get for that? 1.74. Okay. Emails, right? That's the spread. But a better way to think about spreads that you can think about it, you know, with like the 68, 95, 99.7 rule, it's not to think about the variance, but to think about the standard deviation, and they asked for that anyway. So how do I get that? I take the square root. If you write it like this, it'll be a duh, but you need the square root. So take the square root, and what do you get? 1.4. All right, we'll say 1.43. Okay, the last question they asked on this one was what? Help me out. Or is that not what you guys got?
I got 1.2. We took the square root of 1.7475.
Should be pretty close. Let me see what I got. 1.32, yeah. It's okay. We got the right idea, so you're fine. That's a better answer. So. All right, no big deal. So the last question, part C, said do what?
If she spends 10 minutes replying to an email, how long should she expect?
10 minutes for each email. How long can she expect to spend on emails? Well, 29.5 minutes. I agree. Why? Because right here, They asked you, we want to write this the formal way because we're going to work with these a lot today. They asked for the expected value of 10 times each email. And that rule from yesterday is that that 10 comes outside. This is that. So that's why it's 29.5 minutes that the professor can expect to spend each day on emails. Okay, if we did it with our calculator, we'd have done it like this. You do need to know how to do it both ways. So I need to go to my lists. Stat, calculate one variable statistics with list 1 having list 2 as the frequency or probability weights. There you go. And we erased that, but that was there just a second ago. All right, let's look at one more example. It's going to be the big one. Okay, so looking at that final example in chapter 16, I think we need a couple random variables. The first question, we're looking at cars, right? And how long it takes and how much money it costs to do mechanical repairs on average at a shop, and also they also do some cleaning and stuff like that. Okay, so we've got a lot of different things though, because we've got cleaning, we've got mechanical repairs, we've also got how much money is involved, and we've got how much time is involved. So we're going to be combining some different random variables. So we're going to use all those combination rules from yesterday, or most of them. So M, I'm calling my random variable for what? Mechanical time. Exactly, that's what I'm going to start with. Because question 1 asked us for... What did question 1 ask? Find the mean and standard deviation for total time. So, A is mechanical time. I mean, M is mechanical time. A is... I called it appearance time. You could call it cleaning time, or whatever. They wanted us to find the mean and standard deviation of the combination for the total. Well, the total is obviously just going to be M plus A, right? The amount of time you spent on this one plus the amount of time you spent on that one. So we want to find the mean. What's the other word for mean that we've been using? Expected value. So I want the expected value of T. The expected value of T is, in other words, the expected value of M plus A. How do we do the expected value of x plus y from yesterday?
Expected value x plus expected value of y.
Exactly. That's not one you need to memorize. It's just common sense. To find the expected value of one data set plus another data set, you can just find their two individual expected values and add them together. It's pretty simple. So I think they told us what some of those were. What's the expected amount of mechanical time that it takes at the shop? What was it, 90? 90? Okay. So I'm going to try to color code this a little bit. So we got 90 minutes for that, plus 60 minutes for the other one. So 150 minutes. Very simple. Okay. So they also asked us for the standard deviation of that, didn't they? So first I'm going to look at the variance. So I'm going to go the variance of T, which is, in other words, the variance of M plus A. How does that work for yesterday? Remember, we're thinking about spreads now. So we've got the spread in the mechanical time and the spread in the appearance time. And yesterday we said that no matter what, spreads add. Exactly. Thank you, Kinsey. Whatever else? Okay, so spreads add. That's not that bad. So now we've got to be a little bit careful here. How do I get the spread of M? I think they told us a number. What's the number they told us?
15 minutes.
15 was the what?
Was
Standard deviation.
The standard deviation. So do I just put 15 there?
No, square.
I put 15 squared there, right? So this is 15 squared. They told us the standard deviation for appearance time was 5 minutes? Was it 5? So I shouldn't put 5 here, I should put 5 squared. So I can figure that out by adding them together. 15 squared is what, 225? Right? Sometimes I forget that one. I remembered it today. It's a miracle. I think I'm right. Yep. Okay. So I didn't want the variance, so they asked us for the standard deviation because that's the measure of spread we're more comfortable with. We know how to do z-scores with it and all that business, which we're going to do today. We're going to use this for z-scores. So standard deviation of total time is going to be what? How do I take that and turn it into standard deviation? Take the square root. So it hasn't been very hard yet, huh? Maybe none of it is. I don't know. If you guys remember yesterday, we're good to go. So that's 15.8 minutes. Cool? All right. Question 2. Question 2 says, what are the mean and standard deviation, not for the time, but for the money, the expense? Yeah, the expense. So let's define a new random variable. I'm going to keep these in mind, though. So you guys keep those in mind. You might have to feed them back to me in a second. So I'm going to say D. D is total expenses. I didn't want to use E because like E is expected value and it's going to get confusing with all the E's going on, you know? So total expense. Expected value of D. What's that going to be? We're going to have two things, right? So help me fill in these two things. There's going to be a mechanical part and an appearance part, right? Cost for each one. So there's the mechanical part plus the appearance part. I'm leaving some extra space there. Why?
Per hour.
Per hour.
Per hour, yeah. How much money do we spend on the mechanical part per hour at the shop? 50, so I should put a 50 here, right? And then for each hour of appearance time, it's 6. It's really cheap. That's not going to happen in Colorado anymore soon. Have to be political. Okay. So how do we do that? Do we know the rules for expected value there? Yeah, I think we do. These are constants. How did constants work with expected value on that last problem and yesterday? Don't they go like this? There's nothing sneaky in there. So we're going to have 50 and 6. But there's a little tricky part here. That's $50 per hour. The expected mechanical time we had from a second ago, right? Didn't we have it? Was it in hours or minutes? It was in minutes, so we got to convert that to hours.
1 minute.
So it was 90 minutes. So what is that in hours?
1.5 hours.
1.5. Expected appearance time spent was 60 minutes. So what is that in hours? 1. You've got to be consistent on things like that. But that's it for this one. We got it. Nice. This is the expected amount of total expense. Is going to be, what is that, 75? Plus 6 is $81. Cool. So the shop can expect to spend $81 on average to process these vehicles per hour. Does that make sense? We also wanted the standard deviation of that, so let's do that. So we got the variance of D, which is going to be the variance of this stuff. So we said it a second ago, variance is always add, spreads always add, so we go like this, right? Except when you have 6 or 50 inside of a variance, what happens when you pop it out? It's squared. Nice. You gotta square it when it comes out. Oh, and we still have that like hours to minutes thing going on, don't we? So we gotta be a little careful. What numbers am I gonna have to put out here? So what was the variance for minutes? Or excuse me, for mechanical time in minutes? Just look it up. We still have this 50 in here, right? This 50 is in here with this, so 50 has to come out here and be squared, like Ricky said. And 6 is inside there with that, so take it out, you go 6 squared. I guess I said it a little wrong, so my bad. So that's what you have to do first. So those are 2,536. You guys need to help me with the variance of the mechanical time and the variance of the appearance time. So the variance of the mechanical time, what was it? Did they tell us that? I'm looking for it. I'm tired. Oh man. They said 15 minutes was the standard deviation for mechanical time, didn't they? But we can't be in minutes. We got to be in hours. So what's 15 minutes in terms of hours? A fourth. So I'm going to put a fourth here. Except I've got to do something else. That's the standard deviation. So I've got to square it. For the appearance time, the standard deviation was 5 minutes. What's that in terms of an hour? We might need to do some math, right? So 5 divided by 60 is, it's 1/12. So in here, is it 1/12? I don't trust myself today. Yeah, 5 goes into 60 12 times. Okay, so it's 1/12. So what number do I need to put in here? That's the standard deviation. Variance is the standard deviation squared, yeah? Okay, so I'm going to put that in our calculator. I'll just tell you what we get. So I got $156.50 if I want the standard deviation of that business, and it's going to be the square root of that, which is $12.51. Which I think makes sense when you think about the expected value or the middle of where this Z-curve would be. That's not like a crazy humongous spread. It's 12 each direction for one standard deviation in each direction, okay? So now we're going to look at the difference in the costs. So let's look at that one. I'm going to pause this guy. Okay, so my class was instructed to try to figure out the next one yourself. It's really clear. It's really similar to the other one. So we just computed the summation of the two costs, mechanical and appearance. Now you want to find the difference in those two costs and then unpause the video and see if you got it right. So what do you guys think? Am I doing okay? It's the same thing except with a minus, right? So this one comes out 75 minus 6, which is $69. So on average, there's a $69 difference between mechanical repairs and appearance repairs, okay? Am I good to go on this one so far? No, what's the problem? Ah, variances, spreads always add. Good. Am I good to go now? Variances always have like squares in them, right? Like that's the key. If you remember that, you're good to go. Okay, now I think I'm okay. So this is 2,500, right? Just did it a second ago. Variance of M, didn't we have that a second ago too? What was it? In minutes it was a fourth? So it was a fourth squared. And this is going to be 36. And the other one was 5 minutes. 5 minutes was 1/12th hour, so it was 1/12th squared. So then you stick that in your calculator. Who's got it? really need to stick it in your calculator?
No.
No, why Montana? It's the same as the previous one. Whether I add or subtract, the spread isn't going to change on this combination. So I'm going to get this, which was the previous one. Very nice. So standard deviation is going to be the same thing. Take the square root of that. What do we get, like 12 bucks?
$12 difference.
Yeah, okay. So there we go. So the last thing, the final piece in this slightly large problem, says what's the probability it will take longer to do the appearance prep than the mechanical prep? What's the probability it'll take to do those things? And I put a little note in there. I said, what kind of probability model are we assuming here? Is this discrete or continuous land that we're in? Most of the problems we've done so far were discrete, where there was only a certain number of minutes. Is that the way this is? Is there like 2 minutes or 3 minutes or 5 minutes and that's it?
No, it's however long it needs to take.
It's however long it needs to take. There's an infinite number of outcomes. This is continuous, right? So you want a certain continuous there. I said also we couldn't yet answer this question unless we believe these phases each follow a normal model. Do you guys think that the mechanical time, the appearance time, all that stuff, is it fairly symmetric? Is there any reason to suggest it might be skewed? Or like heavily skewed? It might be skewed, like some repairs might take longer. So that's kind of an iffy assumption. We're just going to assume it here. We're going to talk more about that assumption next semester, really. So let's just do it. So if it's a continuous model, what are we going to end up using? Z-scores things. So the question is, we need to translate. So I'm going to write that down. I think we've got all the info we need. That's what we did in 1, 2, and 3. So what's the probability it will take longer for appearance? You need to paraphrase this for yourself. Longer for appearance than mechanical. That's what we're trying to answer. If you're trying to talk to your friend on this, you're not going to be able to do it. So, what's the probability appearance lasts longer than mechanical? How can I say that with like some symbols that we've been using? What do we call appearance time, the random variable appearance time? We called it. This is the probability that A is greater than M. That's one way to state it. How do you do that? Here's maybe the slightly clever part. What are you comparing to? These are two separate random variables. You can't just compare them one to another. So we found combinations of them, right? We did the plus and we did the minus. Why'd we do that? Because we could either go like this, couldn't we? Or go the other way. We could say M minus A and go like that. That's that, isn't it? Which one of these did we spend all our time doing? Because that's the one we want to use. Do we spend our time finding the expected value and the mean for this one or for this one? Either one is fine, but which one do we do? I can't remember. The bottom one, do we do M minus A or A minus M? We did M minus A. So I think we want to use this guy. So there we go. What's the probability that M minus A, turn this around, less than side is less than 0? We have all that information. We don't have to go back and do it again. Z-score time. You've got the distribution of M minus A. It's a continuous random variable distribution. You know its middle because we spent all that time calculating its middle. You know its standard deviation because we spent all that time using our different rules to find its standard deviation. That's the power of what you just did. You guys see how much we're sucking together here from this semester? So the middle of it, what was the middle of the random variable M minus A? What did it end up being? I don't remember. You guys have it? It should be on there. Will, what'd you have? Expected value of M minus A. Did we ever even do that?
59.
We almost did it at the top. We did M plus A, but what would M minus A be? If M plus A was 90 plus 60, then M minus A is 90 minus 60, which is 30. I'll just write it down. Expected value of M minus A. expected value of m. I guess we didn't do that one yet, my bad. We did m plus a, which pretty much the same, so 90 minus 60. Okay, that was easy. I don't know if we really did this either. The variance of just m minus a, we did something like it. I thought we did it already, so my bad. Variance of m minus a, what's that going to be? Help me do it.
The same thing.
Pretty similar, so it's going to be the variance of m plus the variance of a. But Kinsey said we don't even really need to go through and do that calculation because it's going to be the same thing as the variance of m plus a because of what Montana said just a second ago about that other problem, right? We could do it again, I'll write it out, but it's going to be the same. So, very nice. The variance of m was what, 90 minutes?
15.
Oh, it was 15 minutes? Okay. 15, that was the standard deviation. We gotta, should always expect squareds on your variances. The other one was 5? Thank you, Richard. So the thing we want, the standard deviation of m minus a is going to be the square root of that. Can you guys see the Pythagorean theorem in this? I think you should.
Yeah.
That's why this is called the Pythagorean theorem of statistics. What's that going to be? Well, what did we have before, Kinsey?
15 minutes.
15.8. 8 1? 8. Oh, it's just 8.
Yeah.
Okay. So 15 that direction's one standard deviation, 15 that direction's the other standard deviation. What were we interested in answering the whole time? We wanted the probability that a was bigger than m, which we subtracted a to the other side so we could compare it to its finite value, like 0. We turned that around so it's easier to read. This is the distribution of m minus a. Where's 0 on it? Because that's what we want to compare to. We want to see the chance that we're less than 0. 0 over here or over here? We want to know the chance that we're less. The chance that we're less should be pretty small, just like our picture's saying, right? The chance that the appearance time is going to be more than the mechanical time, very small, because mechanical is a lot longer, right? So, z-score. Z equals x minus mu over standard deviation equals negative 30 over 15.8. That's going to be like negative 1 point what? 1.899. So the probability that we're looking for is the probability that z is less than negative 1.899. So you can look that up in the back of your z-score for our class today. I just pulled it out of the book for them, so it turned out to be 2.88%, which is small, matching our picture and our intuition. So that's it on this beefier problem here that we were working with, bringing together a lot of concepts, working with random variables and continuous random variables in particular, where we had to find combinations of variances and expected values in order to achieve that final continuous random variable problem that we wanted to find the probability of. So when you're doing problems like this, don't get intimidated. They're just kind of a little bit long. They're not that long. We kind of did a lot of different things on this one. Usually you're only going to be asked for a couple things. So key, tricky parts are, number 1, make sure that you remember variances always add, spreads always add. Another thing that you don't want to get too tricked out on is make sure you write your probability statement at the end after you've done your combinations. Make sure you do that by writing it out a couple different ways in a way that makes sense to you until you can get not random variables compared to each other, but compared to a finite number, pretty much 0. You're going to be comparing these to 0 in this type of problem. So variances always add, write your statement carefully in terms of 0, and what's the other thing that might be a little bit tricky? I don't know if there is anything else. I think that's about it. So variances always add. Oh, and also variances, you're pretty much always going to be working with square numbers. Okay, I'll see you next time.